Imagine if I told you that one of the biggest climate villains on Earth isn't oil, airplanes, or even giant factories. It's concrete. Yep, the same boring gray stuff under your feet every single day. Doesn't sound very dramatic, right? But here's the shocking part. Cement, the key ingredient that holds concrete together, creates around 8% of all global carbon dioxide emissions. If the cement industry were its own country, it would rank as the third largest carbon emitter in the world, behind only China and the United States. That's absolutely insane. For over 100 years, engineers believed there was simply no way around this problem. Making Portland cement requires heating limestone to temperatures above 1,400 degrees Celsius. That alone burns massive amounts of fuel. But the real trouble isn't just the heat. When limestone reaches those extreme temperatures, it undergoes a chemical reaction called calcination, releasing carbon dioxide that has been trapped inside the rock for millions of years. Even if every cement factory ran on clean solar energy tomorrow, those emissions would still happen because they're part of the chemistry itself, not the fuel. That's like trying to cook popcorn without the kernels popping. It just doesn't work. Now here's where the story gets exciting. China, which produces more cement than the rest of the world combined, realized that simply making cement factories cleaner wasn't enough. Instead of asking, how do we make cement greener? Chinese researchers asked a much bolder question. What if we stop using cement altogether? Sounds impossible, doesn't it? Yet that's exactly what engineers have been working on. Instead of tweaking an old recipe, they decided to rewrite it from scratch. And if this breakthrough scales worldwide, it could completely change how humanity builds roads, bridges, skyscrapers, and even entire cities, while slashing emissions on a massive scale. So, how do you build concrete without the one ingredient everyone thought was impossible to replace? The answer is something called geopolymer concrete. Now, don't let the fancy name scare you, because the idea behind it is surprisingly clever. Instead of relying on Portland cement, this material uses industrial byproducts like fly ash from coal power plants and blast furnace slag from steel manufacturing. For decades, these materials were mostly treated as waste, piling up in landfills and storage ponds. Chinese engineers looked at those mountains of leftovers and saw something completely different: the future of construction. These materials are rich in silicon and aluminum. When mixed with an alkaline solution, they go through a chemical process called geopolymerization. Unlike traditional cement, there's no limestone, no giant kiln heated above 1,400 degrees Celsius, and no calcination reaction pumping ancient carbon into the atmosphere. Instead, the materials form a tough, three-dimensional molecular network that locks sand and gravel together into concrete that's just as strong as conventional mixes. The environmental benefits are huge. Since fly ash and slag are already produced as byproducts, the process turns one industry's waste into another industry's raw material. Instead of digging up fresh limestone and burning enormous amounts of fuel, you're recycling materials that already exist. Life cycle studies have shown this approach can reduce the carbon footprint of concrete by 60% to as much as 90%, depending on the exact mix. That's not a tiny improvement. That's a complete game changer. China has been building dedicated production facilities that manufacture geopolymer binders on an industrial scale. Many of these plants are located right next to coal power stations and steel mills, meaning the waste materials barely have to travel before becoming construction products. Less transportation, lower costs, and fewer emissions. A rare engineering win where almost everybody benefits. Of course, making waste behave consistently wasn't easy. Every power plant produces slightly different fly ash, and every steel mill creates slag with unique properties. For a bridge or skyscraper, close enough isn't good enough. Chinese engineers solved this by developing strict testing and blending standards, ensuring every batch meets structural requirements before it ever reaches a construction site. And just when you think this breakthrough couldn't get any more impressive, researchers found a way to make concrete absorb carbon dioxide instead of releasing it. That's where things get truly extraordinary. By now, replacing cement with industrial waste already sounds like a huge breakthrough. But Chinese researchers didn't stop there. They asked another incredible question. What if concrete could actually remove carbon dioxide from the atmosphere instead of adding more? As unbelievable as it sounds, that's exactly what's happening with a technology known as CO2-cured concrete. Instead of letting captured carbon dioxide escape through factory smokestacks, engineers inject the gas into freshly made concrete while it's curing. Inside the concrete, the carbon dioxide reacts with calcium compounds and transforms into solid calcium carbonate, a stable mineral that becomes permanently locked inside the structure. In other words, the concrete literally traps carbon as part of its own skeleton. Here's the surprising bonus. This process doesn't weaken the material. It actually makes it denser and stronger. A stronger mix often means less binding material is needed to achieve the same structural performance, creating even greater carbon savings. Every concrete block produced this way becomes a tiny carbon storage unit that could remain in service for decades, or even centuries. Imagine millions of buildings quietly storing carbon while doing nothing more than standing there. That's engineering working overtime. And then comes another futuristic ingredient: graphene. You've probably heard graphene described as a wonder material, and for good reason. It's incredibly thin, unbelievably strong, and once cost more than gold because producing it was so expensive. Thanks to advances in manufacturing, Chinese companies are now producing graphene at much lower costs, making it practical for construction applications. Even adding less than 0.5% of graphene oxide to a concrete mix can dramatically improve its compressive strength, reduce cracking, and increase durability. Think of it as giving concrete microscopic armor. Water is one of concrete's biggest enemies because it slowly seeps through tiny cracks, eventually corroding the steel reinforcement hidden inside. Graphene creates an almost impermeable barrier at the microscopic level, helping block moisture before it causes damage. That means bridges, tunnels, and buildings could last significantly longer before needing expensive repairs or complete replacement. And that's a huge deal because the greenest building isn't just one that's built sustainably. It's the one that doesn't need rebuilding every few decades. But China wasn't finished solving problems. Cement wasn't the only resource running out. The world was also facing an unexpected shortage of something almost everyone assumes is unlimited: sand. Here's a fun fact that surprises even engineers. Desert sand looks perfect, but it's actually terrible for making concrete. Years of wind have rounded each grain until they're too smooth to lock together properly. Strong concrete needs rough, angular sand from rivers or quarries. As demand has exploded, illegal sand mining has become a serious environmental problem in many parts of the world. China tackled this challenge from two directions at once. First, demolition waste from old buildings is crushed into recycled aggregate, replacing a large portion of newly mined gravel and sand. Second, researchers developed treatment methods that make sea sand suitable for construction. Traditional concrete struggles with sea sand because leftover salt corrodes the steel reinforcement inside buildings. However, geopolymer concrete is far more tolerant of these conditions, opening the door to using a massive resource that was once considered unusable. Suddenly, yesterday's rubble and coastal sand become tomorrow's skyscrapers. That's recycling on an entirely different level. But perhaps the biggest achievement isn't the chemistry. It's the fact that this technology has moved beyond the laboratory. Geopolymer concrete is already being used in roads, bridge components, precast wall panels, industrial buildings, and sections of high-speed rail infrastructure across China. Engineers have subjected these materials to the same demanding strength, fatigue, and durability tests required for conventional concrete, proving they can handle real-world loads without lowering safety standards. There's also an economic advantage. Since fly ash and blast furnace slag are industrial byproducts that companies often pay to dispose of, they can become inexpensive raw materials when local supply chains are established. That's a rare combination in engineering, cleaner technology that can also be cheaper. When builders can save money while cutting emissions, adoption becomes much easier. Take a step back and look at the bigger picture. China isn't relying on one miracle invention. It's redesigning the entire concrete ecosystem, from replacing cement with industrial waste to capturing carbon inside concrete, reinforcing it with graphene, and reducing the need for freshly mined sand and gravel. Every piece works together to create a smarter construction system. Concrete is the second most consumed material on Earth after water, so even small improvements have an enormous global impact. And these aren't just ideas on paper anymore. They're being poured into bridges, railways, and buildings that people use every day. The next time you walk past a construction site, remember this. The future of building isn't just about making taller skyscrapers. It's about building them with materials that are stronger, cleaner, and far kinder to the planet.